Again, I'll be presenting this paper called Decoupling Task Solving and Output Formatting in LLM Generation. And this work was done jointly with Honian Kang and Professor Nanyun Peng. All right, so let me start with an example. When we ask a model a question, we care about the answer, but the model can express that answer in various ways. For example, for this math problem, the answer can appear as a standalone number on the left, a phrase in the middle, or a value embedded inside a long explanation. So for us, this is easy to read, but for a machine, it is hard to parse, right? And this variability in the form creates a parsing problem. So in order to have structured outputs, people have been stacking prompts together, like task instruction, question, and required output template into the prompt together and passing them to the LLM at once. But this creates a problem, right? This means the LLM has to handle two objectives together at once, right? The first objective is task solving. It has to reason, it has to infer or extract or judge based on the task type. And then the second objective is format compliance, right? It has to emit the required schema, phrase, or template so the result is consumable. And prior works have shown that the format restriction can hurt task performance. So in our work, we want to decouple the format following from LLM generation to best preserve LLM's reasoning capability. Okay. So our starting point is the classic view of control generation through Bayes' rule. We want to decode from an attribute condition posterior that guarantees format compliance. So here, the prior is just the LLM next token probability. And the likelihood asks whether choosing a token in the current step allows the sequence to satisfy the desired attribute in later steps. And in our case, this attribute is format compliance. And the challenge is estimating this future likelihood without enumerating all the possible continuations. And I'll cover this in more detail. And this is an overview of our framework. We call it DecoG, short for decoupled generation. Here we separate out the format constraints from the LLM prompt. Okay. So the task-related input is sent into the LLM, and the format constraint is passed over to this format estimation module, which I will later call it FEM. And here, FEM performs probabilistic look-ahead and estimates how likely a candidate token is to lead to a formatted completion. We combine the two distributions, and we reweight the LLM distribution using the FEM estimated scores, and then normalize to construct the DecoG's posterior for decoding. And the key idea here is to let LLM reason freely and use an auxiliary module, FEM, to control and guide the output into the required format. Okay, let's take a closer look of the FEM module. There's a hidden Markov model, HMM, responsible for approximating the LLM next token probability. And then there's this DFA, deterministic finite automaton, which is responsible for encoding format requirement. Let's start with the HMM first. So the HMM gives FEM a tractable approximation of the LLM next token distribution, so we can do probabilistic look-ahead efficiently. We distill it from the instruction follow responses. Here we take prompts from the natural instruction V2, and then we sample over 1 million completions and then use Baum-Welsh algorithm to train the HMM, and it has more than 4,000 hidden states. So this makes the HMM close to the LLM task condition output. And then we look at the deterministic finite automaton, which is responsible for the format constraints. And here we show how a event argument extraction output template is converted into the DFA structure. All right. So the blue pivots like row A and row B are fixed anchors that move the automaton forward. And between two pivots, you have wildcard regions that can generate different token sequence of different lengths. So we represent this as a flexible branches, and but here all the valid branches they later merge back before you move on to the next pivot. So this allows the DFA to enforce the template structure without enumerating all the possible paths. Okay, so far I've described how FEM look-ahead works, and let me show an example of how it actually steers the generation process. Here is an example of a math problem, and it's asking for the cost of Alex's dinner. And notice that we require the template, the final answer is blah, 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 to be generated. And I'm going to show how the HMM model steers the original LLM generation to the required format. So here I selected two time steps. On the left, you have LLM distribution. In the middle, you have this FEM module, HMM scores. And on the right, you have the final Deco-G posterior that used to generate the sequence. So the word cake is generated during the reasoning part. And then the template word final at the bottom is generated during the final stages. So on the top is when the model generated word cake during reasoning. And here the LLM is very certain, right? You can see the almost 100% weight allocated to the word cake. And the HMM signal in the middle is quite scattered. So when this happens, Deco-G applies a weak control, and then the generation is dominated by the LLM distribution. So the idea is the reasoning trajectory is preserved. But then at the bottom, we see Deco-G steers the LLM to produce a different word. So while the model favors the word total, it also allocates certain probability weights onto other words like answer and final. As we require the template the final answer is, the FEM module assigns a high score to the word final in the middle. So when combined together, it steers the actual output from the word total to the word final. And the takeaway is Deco-G steering behavior is targeted toward required template, and it does not broadly interfere with LLM's reasoning process. And I'll also walk you through how Deco-G steers the generation in the final output stage to guarantee the format compliance. So as the LLM is done with the reasoning in the previous parts, and when it approaches the final utterance, the FEM will steer the LLM to generate the word the instead of other candidates like therefore, so, total. And in the next step, the LLM favors the word total, but then the HMM assigns high score to final, so that it steers it to generate the word final. And as we move on, the format signal becomes sharper in the middle and sharper. So once the template has been generated, the control backs off, right? That the signal in the middle becomes none. And we allow LLM to generate the actual answer on its own. Okay. So now to the experiment part, we tested this Deco-G framework on multiple benchmarks over different domains like math, event argument extraction, and LLM as a judge. And we test against three models, Llama 3.1, Qwen 2.5, and Qwen 3. We compare our method against free generation, structured decoding, and controlled generation with unconditioned HMM. So first, for GSM-AK, math reasoning, the two metrics that we track are format compliance and answer accuracy. And the main result here is that Deco-G guarantees the format compliance 100%, while preserving or improving the accuracy across three models. And then moving on to summary evaluation, the goal is to align the model ratings with human annotations while maintaining the required output format. And here, decoupled generation achieves the best average correlation with human annotation while still achieving 100% format compliance. And finally, we have event argument extraction, sorry, where we evaluate the F1 score over argument groups. And here, Decoupling also achieve better or comparable performance overall. All right, and that is the end of my presentation. Thank you for listening.
All right, do we have any questions from the audience? Okay, I can ask a question.
Sure.
So Deco seems like a very elegant constrained decoding approach. Do you see it as potentially being applicable for other constrained decoding problems? And did you try it out in those settings?
So actually, there's another work from my lab mate, which is called Control R, where he applied this kind of control generation framework onto reinforcement learning to make it explore different paths, right? You can enforce the model to use different reasoning patterns or reasoning frameworks using control generation, so that in the rollout you kind of hit different paths or different thinking. Different ideas. So, which makes the RLVR more diverse and explore different grounds. So, yeah, I think he is also presenting at ICML this year. So feel free to check out his paper.
And was that work also using the reweighting with the HMM approach?
Yeah,
Okay, yeah. Well, now we have some info about what to look for at ICML. Okay, so if there are no other questions, all right, then we would move on to our next paper. Do we